Welcome to Math TV with Professor V. In this video, we're going to learn how to solve problems involving work, in particular, finding the work when you're pumping liquid from containers. I know it's such a specific sort of circumstance, but it comes up in calculus and it can be really tricky. So I wanted to make a whole video dedicated to this topic. So by the end of the video, we're going to be able to solve the following problem. A conical tank is resting on its apex. The height of the tank is 8 feet and the radius of its top is 7 feet. The tank is full of gasoline weighing 45 pounds per feet cubed. That's a little dangerous, all that gasoline. How much work will it take to pump the gasoline to the top? Give your answer to the nearest foot-pound. So that will be the grand finale of this video. We'll solve that problem. But before we do, I need to lay a little bit of groundwork. If you haven't already watched the basic introductory video lecture on work, I'll link it here. Just click the top right. It'll be in the description as well. But I'll just give you a brief recap in case you don't feel like it, so we can just get the ball rolling on these problems. So work is based first on the idea of force, okay? Force is a push or a pull on an object. And if you've taken a little bit of physics, hopefully you're familiar with that topic. If not, this will just be really basic. Force is equal to mass times acceleration. We know this is the second derivative of the position function with respect to time. So that's acceleration right there. The biggest thing to keep in mind are the units for force, okay? And it depends on which system you're working in. If you're in the metric system, the units for force are newtons, and you just write an N. But newtons are equal to 1 kilogram meter per second squared. So the combination of a kilogram times meters per second squared gives you a newton. That is crucial for doing these problems. And then you can see here, mass has to be in kilograms, and then acceleration would be in meters per second squared, okay? Now, when you're in the US customary system, sometimes it's called imperial, the unit for force is pounds. That's it, pounds. We don't talk about mass typically in the US customary system. So this can be a little confusing when you're solving the problems because the setup, there's one extra step when you're working in metric compared to US customary system. I'll emphasize it when we get there, but just know the difference between the units. Pounds versus newtons. Newton is comprised of kilograms times meters per second squared. Now, what is work? Well, work is performed on an object. It's the force that's applied through a distance, through a displacement. And when acceleration is constant, force is also constant, as long as mass is not changing, right? So if this is constant, this usually doesn't change, then force is constant. And we have the following formula for work. It's equal to force times d, distance, displacement, depending on the problem. Okay. What are the units now for work? Well, it depends. If you're in the metric system, the unit is a joule, which we abbreviate with just a J. So work would be a joule, which is a newton times a meter. Okay, you don't write newton meters, it just becomes a joule. The US customary system, it's a foot-pound, and we don't have a cute abbreviation for it. You just write foot-pound. Okay, but basically you can see this is force, distance. Yes, then this one's backwards. Force, distance. Okay, that's the unit for work. When force is not constant but variable, then we use the following formula, which is a definite integral. So work is given by the integral from a to b of f of x dx. And what are a and b? Well, it's the location of the object. So it would be, this integral represents the work to move an object from A to B. So I've done some other examples in the previous video where you would use this formula. It applies with Hooke's law, with springs. Also, if you're like rescuing somebody and lifting them, with a rope, the force is variable, and you're just moving them from A to B. So this formula would apply. However, I told you we're solving a different, very particular kind of problem in this video, and namely that is we're going to be pumping liquid from containers. Gasoline, water, oil, what have you. So how do you find the work in this scenario? It's a little bit of a different setup. So here's how it starts. Work we know is force times distance, okay? You take your container, say I just have a nice cylindrical container. We're gonna start off really relaxing, okay? You're gonna take your container and pretend it's full of some purple liquid, say Jello. And then we're gonna slice it up. We're gonna partition it. And I want to figure out what is, this is going to be my ith layer or slice. And I want to know what's the work required to move that ith layer out of the container. Okay, so here's how the setup works. We're going to figure out what is the force required, right, to lift the ith part times the distance that the ith part has to move to get out of the tank. Force times distance is work. I have how many little layers? I'm going to partition I equals 1 to n and then add them all up. And then I want no error, so I take the limit as n goes to infinity. You probably haven't looked at this sort of setup since you first learned integrals, right? And you studied Riemann sums, but that's where it's basically coming from. So once I take this limit, I'm going to end up with the integral from a to b. The force for the ith part always works out to be some sort of f of x times delta x. You'll see why. The distance the ith part moves is going to be a function of x or y. You could do it either way. So then I'm going to have f of x. I have a d of x, distance that each layer moves, and then delta x becomes dx in the integral. So let me color code for you because I know it can be overwhelming. F of x is here. Delta x becomes dx in the integral. And then you have this one extra term. It seems, but not really, okay? So what's confusing is when students see this formula for work, they think that's what we're applying when we're pumping liquids, but it's not. This is just moving one object from A to B. The reason this ends up being an integral is because we partition all of the liquid up into a bunch of little baby pieces, and then when we add them up and take the limit, that becomes an integral. But this is still force times distance, so you need force times distance, and then adding them all up, there's the integral. Okay, so these two formulas are not for the same scenario. That's why there's this additional little distance component that is not here. That's for a different kind of problem. Okay, again, most of the time we pump the liquids vertically. So if you want to use y to represent the height instead of x, you can, and that's what I'm going to do for these problems. So the formula I'm going to use looks more like a to b, f of y, d of y, and then dy. But x's or y's, it doesn't matter. Okay, are you ready? It's going to feel a little overwhelming at first, and then you'll be fine. I'm going to give you step-by-step method. Here we go. A vertical, right, circular, cylindrical tank measures 20 feet high and 12 feet in diameter. It's full of oil weighing 60 pounds per foot cubed. How much work does it take to pump the oil to the level of the top of the tank? Give your answer to the nearest foot-pound, which I won't. I'm going to leave it in terms of pi. I'm going to be disobedient. Okay, so yeah, I had a student ask yesterday, like, this is just a lot of verbiage, right? Vertical, right, circular, cylindrical tank. Okay, circular means base and height are circles. Vertical right means that it's not a slanty one, okay? So the height is perpendicular to the base, I'll show you right now. It's 20 feet high, 12 feet in diameter. So the radius is 6 feet. Here's the height. That's 12 feet. And right meaning it's like this. Sometimes you'll see a slanty guy. We're not in that scenario. They wanted you to rest assured that's not what we're dealing with, okay? It's 20 feet high, excuse me. I got entirely too excited. Over here, right? It's 20 feet high. There we go. Okay, 20 feet. Ba-dum, ba-dum. So what I'm gonna do is start off labeling. This is y equals 0, okay? I'm starting from the ground up. And this is full of oil, so imagine, you know, there's all this oil in there. And I'm gonna slice up or partition all of the oil in this tank. So I'm gonna cut it up into a bunch of layers. Let's call this layer y sub I right here. And then up above it, this would be y sub I plus 1. I'm gonna go into a lot of detail with this first example, and then you can kind of like gloss through it once you get the feel for the setup. Okay, so here is one layer, and I want to figure out the force needed to lift this layer out of the tank. So first look at the problem and tell me what units would force be in. So notice here we're in the US customary system. It's feet and pounds. So force in this problem is in pounds. Write that down immediately, okay? So the first thing I need is the force required to lift a layer out. I'm gonna get there step by step. Step 1, find the volume of this ice layer. So I'm gonna write V sub I. Sometimes you'll see delta V or whatever, or you can just write V, it's not that big a deal. What's the volume of this little ice layer? Well, look at it. It's got a circular base times the height. Circular base would be pi r squared times the height. Now the radius of this slice is 6, right? We established that earlier. So V sub I would be pi times 6 squared times, what's the height? Well, the height is the change from y sub I to y sub I plus 1. It's delta y. That's my height. Delta y. So V sub I is 36 pi delta y. And please put some units on it. This is the key. So I need units for volume. Volume units are always cubed, and everything's in feet. So pi r squared h would end up as feet cubed. Good? That's step 1. Get V sub I. Always start with volume, always, for these problems. Okay, what's the next step? I want to figure out what's the force required to lift the ice slice of oil. Was it oil? Yeah. And this is where you come back and you use the given information here that oil weighs 60 pounds per feet cubed. Notice the units, pounds, that's force per feet cubed, that's volume. Beautiful. So I take my V sub I, 36 pi delta y, I do recommend writing the units, and then you multiply by 60 pounds, I would put per feet cubed in the denominator like so. Then you can see so clearly, bam, bam, these units cancel out. It's most satisfying. And what units will I be left with? Pounds. Isn't that force? Beautiful. So then you're just going to take 36 pi times 60. So that's 2160 pi. And then we still have delta y pounds. Boom. So now we have force. So now I have that first chunk of my integral. The next part I need is the distance that that layer, the ice layer, the one at y sub I, moves to get out of the tank. Okay? So let's think about it this way. The layer that's all the way at y equals 0, how far does it have to move to get out of the tank? 20 feet, right? What if it was at y equals 1? How many feet would it have to move? 19. So whatever its height is, whatever y sub I is, it moves 20 minus y sub I. Once we put it in the integral, we'll drop the I subscript. It's just going to be 20 minus y. Okay, we're ready to roll, people. I know it may not feel like it, but we certainly are. So here we go. Work is going to be, put all this together, work equals. We'll talk about the limits in just a second. I have 2160 pi. Delta y becomes dy in my integral, and then I have 20 minus y. I'm going to color code for you right now, don't worry. 2160 pi, here he is. Delta y becomes dy, and then 20 minus y right here. Now, as far as the limits of integration, it has to represent all of the liquid that you're moving, okay? So I'm moving liquid that starts at y equals 0 all the way up to y equals 20. So my limits should go from 0 to 20. Boom. Okay, how are we doing? Now, as far as integrating, I always encourage my students, if there's some random constant, take it outside the integral. That way you can just focus on the calculus and not be intimidated by these large numbers. 20 minus y dy. Don't you feel instantly better? I do. Okay, keep that 2160 pi out there. Antiderivative of 20y minus 1/2 y squared from 0 to 20. And then this is going to be 2160 pi. 20 times 20, that's 400 minus 1/2 times 400 again minus 0. This is 200 times 2160 pi, 432,000, so 432,000 pi foot-pounds. Don't forget your units, okay? Very good. How was that one? We'll do a few more, so don't fret. This was just you getting started. We'll do another pretty straightforward one. Here we go. Example 2. The base of a rectangular tank measures 7 feet by 14 feet. The tank is 17 feet tall, and its top is 10 feet below ground level. Ooh, kind of like a coffin. It's buried below the ground. The tank is full of water weighing 62.4 pounds per feet cubed. How much work does it take to empty the tank by pumping water to ground level? Give your answer to the nearest foot-pound. So this time we just have a rectangular tank. Okay, not too bad. And they gave us the dimensions. Ooh, that looks better. And the tank is 7 feet by 14 feet and 17 feet tall. Okay, so then I'll say this side is 7 feet, this side is 14 feet, and it is 17 feet tall. And then it's also 10 feet below ground level, the very top. So there's another 10 feet here, and then this is up here, this is ground level. Okay. So there's 10 feet of nothingness right below ground level, like just dirt, let's say. Dirt, sand, what have you, okay? So how much work does it take to empty the tank by pumping water to the ground level? No problem. Let's remind ourselves, what is the unit of force in this problem? It's going to be pounds, okay? Write that immediately. Very good. So we're going to start off the same way as the other problem. I'm going to partition everything, okay? Let me move, let's see, I'll put the 7 feet over here so that this side is nice and clean for me to write on. Okay, I'm going to call all the way down here y equals 0. I think in the last video I did x's, but you know, whatever. So here I'm going to have at some height y sub I. I'm going to slice up the water. Pretend you can slice up water, and that makes sense. Okay, and then y sub I plus 1 would be a wee bit higher. I don't want to make it too thick because these slices are supposed to be little, but then like I want you to see nicely, you know. So maybe they're a little thicker than standard, but hopefully the picture helps. Okay. Yeah, I like it. That's y sub I plus 1. Y sub I. Okay, let me color it in. Here's the slice. Here's the slice. Yeah? And then just do a little bit this way. Okay, let's not get it too wild here. So, step 1, always find the volume of the ith slice. What is the shape of the slice? It's a rectangular slice, so the volume would be length times width times height. The length and the width, let's see. Length is 14. Width is 7. Height, remember, the height is always for these guys delta y or delta x. Yeah, you won't have a constant. So it's going to be 14 times 7 times delta y. In the last problem, it was the same thing. It was pi r squared h. H was delta y. Same thing here. So this is 98 delta y, and then it's imperative. What are the units for volume? Length times width times height, feet cubed. Volume is always going to be something cubed, either feet cubed or meters cubed. Step 1 is done. Step 2, I need to figure out what's the force required to lift that ith layer. So this is where you're going to use the info given that water weighs 62 pounds per feet cubed. 62.4, excuse me. So 62.4 pounds per, put the units in the bottom because then you can have your little mini cancel party. 98 delta y feet cubed. What's the cancel party? It's happening right now. Bam, bam. Okay, so 62.4 times 98, this is going to give us 6,115.2 delta y pounds. So now that's force, okay? Good. I don't know, can you guys hear? My ice maker's going wild right now. Sorry about that. Okay. Confirm. Is it force? Yes. Units are pounds. That's what we said we were working in this problem. Beautiful. Then I also need to know what is the distance that the layer at y sub I needs to move, right, to get out of the tank. So this one's a little funky because the tank is below ground. So let's think about it this way. The layer at y equals 0, how far does it have to move to get all the way out? 27 feet, right? 17 for the tank and then another 10 if you're at y equals 0. If you're at y equals 10, how far do you have to move? You'd have to go 7 and then another 10, 17. So whatever layer it's at y sub I, it's going to move 27 minus y sub I, or 27 minus y when I put it in the integral. Okay? Here we go. So let's set it up. Work is going to be the integral. I have 27 minus y times 6115.2. Delta y becomes dy. And then what are the limits of integration? Only where the liquid is that you're moving, that you're pumping out. So the limits are going to go from 0 to 17. There's no liquid here that you're going to slice up and partition, right? The limits are for y. Y is just from 0 to 17, not up here. No liquid there, so there's no work to perform. 0 to 17, okay? Good. Take this constant out, please. 6115.2, integral 0 to 17, 27 minus y dy. And then hopefully now you're home free, right? Usually these integrals are just going to be polynomials. They take pity on your poor soul that the setup's so hard, so you don't do anything much more than that. 0 to 17, blah, blah, blah. It's not interesting. So I'll just cut to the chase. You should get 1,923,230 foot-pounds. Okay. All right, very good. Very good. I'm going to do one from the textbook that was in the homework, okay? And this one is going to be in the metric system. So there is one additional step, okay? Example 3. A tank is full of water. Find the work required to pump the water out of the spout. And you do need to know that the density of water is 1,000 kilograms per meter cubed. I will give my students that. I don't know if your teacher will. So what are the units of force? Notice we're in the metric system. So the units for force are newtons. Do you remember what a newton is comprised of? It's kilograms times meters per second squared. Okay, and then in order to introduce meters per second squared into the problem, we have an extra step, because when we were given force in the previous problem, it was pounds, right? And already everything was set up so that it was in terms of pounds. Here we're going to have to take a little detour through the land of kilograms of mass and then get to force. So think about it. Whatever mass you have, in this case it's just a bunch of water, the force required to lift it out of the tank is the force that it takes to overcome gravity. And what is the force, or what is acceleration due to gravity? Excuse me. Acceleration due to gravity is 9.8 meters per second squared. Depending on your teacher in your book, you might use 9.81 instead. On my test, I don't let them have a calculator, so I tell them just use 10 for gravity, but I'll put that on the exam so they're not nervous about doing it. So just check with your instructor. So these two things, hopefully they're given to you, but if not, make sure you know them, okay? And then the units. The setup's going to be the same. So here we go. I'm going to call this y equals 0. And then we're going to slice it. Let me straighten that out. Straight. Does that look good? Yes, Professor V, we love it. You're doing great. That's y sub I. Then I'll put y sub I plus 1 here for clarity. Okay. And then this is going to come here and here. Oof, not my best work. Actually, no, it looks good. Here we go. Let me shade this side in. So the first thing we have to do is find v sub I. All right. So this is, look at the slice. What is the shape of it? It's a rectangle, right? So step 1, v sub I, volume for a rectangle, length times width times height. Yeah? Okay, so the length I can see, it's from here to here. No matter where I slice, if I slice here, if I slice here, that length is always going to be 8 meters. So that's 8 times, what's the width? Now this is where it gets a little tricky, because the width at this slice is different than the width at this slice is different than the width at this slice. Can you see that? It's changing. I'm going to put a question mark for now. And then the height. Do you remember what I told you the height always is? That's right. It's always delta y. So how am I going to figure out the width? And I need to figure out the width in terms of where the slice is happening, at what level I'm slicing, at what y is. It's not that big of a deal. You're going to draw yourself some triangles and all will be revealed to you. Okay? So I want to know, zoom in. I just zoomed in for you, so I guess that's not too bad. Look what's going on over here. Come on, give me a nice triangle. Beautiful. At this layer, I'll stick with the pink. At this layer, the height here is y, and I want to know what is the width, right? So if the height here is y, I want to know what is the width. Well, look at this larger triangle. Which one am I referring to? This one right here, okay? The height all the way up and down is 3 meters. And what's the width? All the way across. Did you catch it? They gave it to us so sneaky in the back of the picture. It's 3 meters across. And so you see how this little baby triangle is nested inside of the larger one? That means they're similar triangles. So the sides are in proportion. Okay, so since the height is equal to the width of the larger one, the same must be true here in this baby one. If the height is y, then the width all the way across here is also y. Fabulous. Okay, so then instead of a question mark, I'm going to put a y there now. So v sub I is 8y delta y. Ooh, this is where it's tricky. Please tell me the units. Volume is always going to be something cubed. In this case, we're in meters. So meters cubed. All right. Now, before we move to the next step, which is always the force required to lift one slice, because we're in the metric system, we have bonus step. Bonus step. Okay, so we're going to multiply by the density of water. So let's get the mass of one slice. This is the bonus step. We didn't do mass in the last problem, right? Mass of one slice is going to be 8y delta y meters cubed. And then I multiply by the density of water, which is 1,000 kilograms per meters cubed. Okay, meters cubed cancels. Fabulous. Yes, I have mass, not force just yet. It's just mass. This is going to be 8,000 y delta y kilograms. Okay, are you keeping track of what's going on? So right now I'm in kilograms. Step 2, now I'm ready for step 2. I want to figure out what's the force required to lift one slice. Well, remind yourself, what are the units of force? You know that they're newtons, right? And newtons are comprised of kilograms times meters per second squared. I've got the kilograms part. I'm missing meters per second squared. This is where you bust out acceleration due to gravity. Boom. That's in meters per second squared. And that's what we need to overcome, acceleration due to gravity, to lift the water. Perfect. So you're going to take that bonus step answer, 8,000 y delta y, I would put the units on kilograms, multiplied by acceleration due to gravity, 9.8 meters per second squared. Nothing cancels, but you go, I have kilograms times meters per second squared. All of that together is a Newton. Woohoo! And then 8,000 times 9.8 is going to give me 78,400 y, and then don't forget there's still delta y. And if you're in my class, don't worry, I changed the numbers dramatically for the test, so it'll be easy to do. And I'll let you use 10 instead of 9.8 and all that stuff. Okay, now we're proceeding as usual. What's the distance that the layer y sub I needs to move to get out of the tank? Okay, a little funky twist here. It's full of water, which is the first 3 meters of the tank, but there's this extra spout. So the layer of water at y equals 0 has to go 3 plus another 2 meters to get out. 5 meters. The layer that's at y equals 3 only has to go 2 meters. So whatever its height is in terms of y, it has to move 5 minus y sub I, or 5 minus y in the integral. Okay? Very good. So now let's set up our integral. Work is going to be, I have 5 minus y times 78,400 y. Delta y becomes dy. And then the limits of integration are only from 0 to 3, only where there's actual liquid to move. There is no liquid from 3 to 5. Take this 78,400 out, please. So 78,400, integral 0 to 3. And then you see I have 5 minus y times y. So that's going to be 5y minus y squared dy, right? Good. So 78,400. Antiderivative is going to be 5 halves y squared minus 1/3 y cubed from 0 to 3. So 78,400. That's 5 halves times 9 minus 9 minus 0. This is going to give me 45 over 2 minus, this will be 27 over 2. So you should get 39,200 times 27, which is 1,058,400 joules. Okay. I think the back of the book rounds and puts it in scientific notation, 1.06 times 10 to the 6 joules. Whatever, who cares? Good? All right, I promised you we would solve that problem that I posed at the very beginning. So now we're ready for the grand finale, example 4. A conical tank is resting on its apex. Woo, okay. So it just means you have a cone upside down. All right. It never makes a cute ellipse when I want one. There we go. Heavens to Betsy. Straighten up, you. Okay, are you reading the problem while I fiddle with this? Good. The height of the tank is 8 feet, and the radius at the top is 7 feet. So it's resting like this. The height is 8 feet, and the radius at the top is 7 feet. So this is 7 feet. This is 8 feet. The tank is full of gasoline, weighing 45 pounds per feet cubed. How much work will it take to pump the gasoline to the top? Give your answer to the nearest foot-pound. So what are the units of force in this problem? That's right, pounds. Okay, very good. So we're going to proceed as usual. I'll call this y equals 0. And then let's slice her up, partition. I'll say right here, that's y sub I. That's y sub I plus 1. Oh my God, that looked so wobbly. Hold on. Oh, better. I wouldn't have respected myself if it didn't look at least somewhat decent. Okay. So this is y sub I. This is y sub I plus 1. Yes. And we need to figure out v sub I, the volume of this ith slice. Okay, so v sub I, notice this is going to be a circle. So pi r squared times h. What's h? Always. H is delta y. Always, always, always for these problems. Okay, so v sub I is pi r squared h. So that's going to be pi r squared delta y. But what's r? Look. Depending on where the height is, where I'm slicing, like this is r here, yes? But if I sliced up a bit higher, r changes. R is going to be bigger. So I want to figure out what's the relationship with r and the height that I'm at, y sub I. And again, we're going to use similar triangles. Are you ready? Oh, good. Okay, so let's zoom in. I've already zoomed in. Here's the radius. Here's the height. Technically it's y sub I, but you know, yeah. And then that is nested inside. So this is the triangle right here. Shall I highlight? Boom, boom, boom. That is nested inside this larger triangle here. Ooh, okay. Ba-dum, ba-dum, ba-dum. And the radius at the very top is 7 feet and the height is 8 feet. So similar triangles are in proportion. So we can set up a proportion, corresponding sides. So R over 7, baby triangle to big triangle, is equal to Y over 8. And I'm trying to solve for R in terms of Y, so just multiply the 7 over. R equals 7/8 Y. Okay? So I'm going to plug that in right here. And then now we're ready to proceed. So V sub I equals pi times 7/8 Y squared delta Y, which is going to be 49 pi over 64 Y squared delta Y. What are the units? It's V sub I volume. It's going to be cubed always, feet cubed for this problem. Okay, no bonus step. We don't have to go to mass next. We're going to jump straight to force. So step 2, what's the force required to lift that ice layer? So we have 49 pi over 64. Whoa, where did that come from? Y squared delta Y, put the units in, it'll be fun. And then come back here. What am I going to use? That gas weighs 45 pounds per feet cubed. All right. 45 pounds per, put that feet cubed in the denominator. So then you can have this lovely canceling moment. You can have the confirmation that we are in pounds now. And then you just got to multiply all that nastiness out. 49 times 45 is 2,205. Leave the pi over 64 Y squared delta Y. Oh, put the units. I almost forgot. Pounds. Okay. And then last thing, step 3, I need the distance that the layer at Y sub I moves to get out of the tank. Nothing weird happening here. There's gas all the way to the top. It's going to move 8 minus Y. Okay, so put it together. Work. We're going to perform work from 0 to 8. It's full of gasoline. And then I have 8 minus Y. Are you guys okay? I'm just going to throw this constant outside immediately. Immediately. Why fiddle with it at all? It's exiled. 2,205 pi over 64. Then I have Y squared, and then delta Y becomes dy. Okay, next step, you're going to distribute. You leave the nasty constant alone. It's being banished where it ought to be. Over 64. Oops, I got too excited. I was going to integrate already. I guess you could if you're ready. 8y squared minus y cubed dy. Good? Okay. 2,205 pi over 64. This is going to be 8/3 y cubed minus 1/4 y to the 4th from 0 to 8. And then I did fiddle with this. I didn't want to reach for my calculator until the bitter end. So I noticed this was fun. If I put 8 in for y, 8 cubed times another 8 is going to give me 8 to the 4th over 3 minus, and then again I have 8 to the 4th over 4 minus 0. So you can factor out that 8 to the 4th. 2,205 pi over 64 times 8 to the 4th times, I'll have 1/3 minus 1/4, which is 1/12. And then I just started getting all sorts of carried away because 64 is 8 squared. So I canceled that and then I made that 8 squared. And then I just kept canceling my little heart out. But then I did need to break down and get a calculator. So the final answer, we'll leave it in terms of pi. I know, what did they say in the beginning? Nearest foot pound? No. 11760 pi foot pounds. Okay. I think the practice test, you guys, they multiplied by pi. So it has a slightly different answer, but I know you don't have a calculator, so you could leave it like this on an exam. But it wouldn't be such gross numbers, like I keep telling you. Cute little numbers, I promise. Okay? That concludes the video. I hope it was helpful. This topic is always weird for students because I think the setup is unique. And it involves an integral, but it's not the kind of work integral that is taught in the lesson. So it's super confusing. And then whether you're doing it in the metric system or imperial US customary system affects the process. You have one whole extra step. If the video was helpful, please give it a thumbs up and leave me a comment down below. If you made it to the end, be like, woot woot, I made it to the end. I'm putting in the work. Subscribe if you haven't already. I have full-length video lectures for Calc 1, 2, 3, Pre-Calc, Trig. I have a good chunk of videos, but not complete, for linear algebra and differential equations. If you're a member, you can also join my Patreon, get exclusive content, worksheets, other additional videos. You can ask me questions on there. And I'm also on Instagram and TikTok, Math TV with Professor V. Thank you guys for your support. I'll be back soon. Bye.